This week's lab, we had to record, observe, and analyze an object with constant velocity. I chose to observe a tennis ball being rolled across a table as my object in motion. There are two main physics principles present in this experiment. The first being Newton's first law. An object moves in a straight line and at constant speed except that it interacts with another object. In this scenario, forces acting on an object are opposite but equal. The net force will equal zero as well as the acceleration. The forces are balanced in this scenario. The second physics principle present is Newton's second law, which is the change in velocity over the change in time equals the net force divided by mass. The derivative of the change in velocity over the change in time will give us acceleration and a second form of Newton's second law, which is net force equals mass times acceleration. This shows a proportional relationship between force and acceleration, which tells us that net force and acceleration will point in the same direction. In this scenario, forces are unbalanced. It is my prediction that the tennis ball will uphold Newton's first law of motion. With forces present being balanced, the ball will demonstrate constant velocity and closely match the computer simulated model. My initial conditions were recorded and inputted into the video analysis of the mass of ball, diameter of ball, the coordinate system, as well as a point of mass throughout movement and a start and stop time. As we observe the video, here we see the coordinate system set up as well as the diameter and the point of mass present, a start and stop time. Through just observation of the video itself, it appears that the object, the tennis ball, is moving in constant motion. Tracker also provides us with a video simulation and a graphical representation. This graphical representation, as you can see, is a linear line. This also implies that the constant motion and constant velocity. However, to be sure, I will use VPython to set up a computer simulation of the object in constant motion to compare with my video analysis. So I must transfer my initial conditions over. Here all code will be written in red. The initial conditions will be the system's mass, as well as the initial position obtained from tracker in the video analysis, the initial velocity upon which we use the first 2 points of the video analysis to obtain initial velocity, a start and stop time. We also have to put in our net force. To simulate constant motion, net force has to be equal to 0, and we set our vector equal to 0. We also need to input our physics principles. As you can see, we put in Newton's second law. We use the format of the velocity formula, which is final velocity will equal initial velocity plus net force divided by mass times delta t. As well as we use our position update formula, which we derive from the average velocity equals the change in position over the change in time. As we run the model, we will see a graph produced from the computer simulation. As you can see, this graph closely matches our graph from tracker. However, let's plot them together for further analysis. In this scenario of model versus experimental, our model is our computer simulation and our experimental is our video analysis. As you can see, the model and the experimental closely follow each other, especially in the beginning. Towards the end, the graphs diverge slightly from one another. Overall, our experimental data proved to be a fairly good representation of constant velocity. The discrepancy at the end of the graphs can be attributed to the table upon which the ball was rolled being uneven. Since we only analyzed motion in the x direction, the uneven table caused the tennis ball's movement in the y direction, which can account for the error in the graphs. What if we change the coordinate system? If we change the coordinate system, it's arbitrary, so flipping our axes will have little impact on the data. In fact, all data will remain the same. The only change will be in the graph being flipped. However, the meaning of the graph will remain the same, and the straight line integrity will still be present, showing constant velocity. In our computer model, we set net force equal to 0, but how many pushes and pulls were present in our video analysis to account for a net force equaling 0 in our observed video? There are two forces present, the first being gravity pushing down on the ball, and the second being the table pushing up on the ball. However, these forces are equal but opposite. This is Newton's first law. The forces are balanced, which makes net force equal to 0. And if net force equals 0, Newton's second law tells us that there will be no acceleration.